Hi, we are researchers from Carleton College and Northeastern University. Today we'll be talking about our paper, Game Clustering Generation using Gaussian Mixture VAEs. Let's begin with a PCGML question that motivates the entire paper. So given a dataset of 2D platformer chunks, how can we first assign them to K-clusters based on their inherent similarities and differences, and then generate novel chunks from specific clusters? In this paper, we tried to achieve these two goals in the context of three classic platformer games shown in the bottom. So we have Super Mario Bros., Kid Icarus, and Mega Man. The goals on the last slide naturally imposes requirements on the machine learning model that can be used. Let's start with some notation first. Let x be the chunk, y be the cluster index, and theta be the parameters of the ML model. So the goal of clustering means that the model must learn the density of y given x in order to do cluster assignment. In addition, the goal of conditional generation means that the model must learn the density of x given y for sampling novel chunks. The subscript of the function p's, theta, just means that the functions are parameterized by theta. In our paper, we used a deep neural network called the Gaussian Mixture Variational Autoencoder, or the GMVAE. VAE has its own literature, so we won't talk about the theory behind everything today. Instead, let's first understand its training process, and we'll briefly touch on how it satisfies the two requirements we mentioned just now. Any deep neural network is trained by alternating between forward passes and backward passes of gradients. Let's first consider its forward pass. So here we have the input vector, shown in green. It goes to the encoder into its latent normal distribution, from which a latent vector is sampled and decoded into the output vector. The backward pass here optimizes the weights such that the forward pass achieve lower reconstruction loss. But apart from this main branch here, there's kind of this auxiliary branch down here, right? As training goes, two things happen to this auxiliary branch. The model may find that assigning reasonable labels to the input vectors improves the reconstruction performance. So what I mean by this? The label, as you can see here, which is appended to the input vector, acts as extra information that helps the encoder. The dimension of the label is preset and depends on the number of clusters we want. And intuitively, the label is most informative when it's most differentiating, which means that it assigns similar chunks the same label and dissimilar ones different labels. And second thing that happened during training is that the latent distributions of similar chunks tend to be closer to each other. Right? This is the whole idea of dimensionality reduction. We also mentioned that similar chunks tend to have the same label, right? Just in about a minute ago. So over time, this prior assigning network is encouraged by this KL divergence loss to map each label to the average of the latent distributions of chunks that are assigned to that label. Now let me repeat again. So this prior assigning network is encouraged by this KL divergence loss to map each label to the average of the latent distributions of chunks that are assigned to that label. So let's look at some implications. So suppose training has finished. Let's focus on the part of the model marked by the green arrows. So this green arrow and this green arrow. We mentioned that the label assigning network assigns similar chunks the same label and dissimilar ones different labels. Therefore, it's essentially a classifier, which allows us to model the probability of y given x. In other words, the probability that the chunk x belongs to the cluster with index y. Let's focus on another part of the model, again marked by green arrows. Note that this part has a label as its input and outputs a chunk. It first generates the latent distribution, that is the average of the latent distributions of chunks assigned to that label. From this average distribution, a latent vector is sampled and decoded into a chunk. In other words, it allows us to sample a chunk x given some cluster index y. So far, we see that GMVAE does in fact satisfy the two requirements. Let's see some results. So first, let's try visualize some conditional generations. In this part, we trained 3 10-cluster GMVAEs, one for Super Mario Bros., one for Kid Icarus, and one for Mega Man. Here we're only showing the conditional generations for Super Mario Bros. Due to space limit. As you can see, there are 10 columns, each corresponding to one cluster. And in each column, we show 6 examples of generated chunks and then a radial bar plot of the tile densities. Note that the tile density of a specific tile is normalized across clusters for comparison purposes. So here are our main observations. First of all, each cluster indeed captures specific patterns. So, for example, radial bar plots of cluster 2 and 5 show high pipe density. So, by the way, pipes are encoded by this character, this character, this character, this character, and this observation can even be verified from the generated examples. So here you see a lot of pipes, and here you see a lot of pipes. Radial bar plots of cluster 4 and 6 show high ground tile density. So by the way, ground tiles are encoded by the capital X. And this corresponds to the staircase design pattern shown up here. But visually, we still see some patterns span multiple clusters, and each cluster may contain multiple patterns. There are 2 possible reasons for this. One is that the right clustering is not clear for chunks unlike handwritten digits. Another reason is that the clusters are optimized for reconstruction loss instead of their perceptual differences to humans, and that is in fact one of our limitations. So now let's talk about ways for us to evaluate GMVAE. So the first way is to use a labeled dataset. In Super Mario Bros., the most obvious inherent structure is the level type. There's 3 level types: overworld, underworld, and jumpy levels. They all look different in terms of color scheme here, but they were all encoded using the same tiles. So their real differences are overworld levels have ground tiles at the bottom, despite occasional breaks for jumping. Underworld levels have ground tiles at the bottom and breakable brick tiles at the top. Jumpy levels have platforms floating in midair. We trained GMVAE with 3 clusters on Super Mario Bros. After balancing for the number of levels belonging to each level type. We also trained a vanilla VAE on the same training data as the baseline. We then used TS and E to project their latent vectors to the 2D space. So the 2 plots on the left are about GMVAE. Here we see the latent vectors colored by true labels: underworld, overworld, and jumpy. Here we see the latent vectors colored by assigned clusters: cluster 1, cluster 2, and cluster 3. The 2 plots on the right are about VAE. Here we see the latent vectors colored by true labels, and here we see the latent vectors colored by assigned clusters. But note that VAE itself can't do clustering, right? So we had to train an additional Gaussian mixture model on top of the latent vectors to achieve such result. Clearly, the GMVAE assigned clusters in a way that's closer to the true clustering. Also, the learned clusters are better separated. On the other hand, since VAE imposes a unimodal Gaussian prior rather than a Gaussian mixture prior on its latent space, its latent vectors are tightly squeezed together, making it difficult for the Gaussian mixture model to separate. Therefore, it's perhaps not surprising that GMVAE achieves a significantly higher clustering accuracy than VAE GMM. And so by VAE GMM, we mean the hybrid model of training a GMM on the latent vectors of the VAE. Generally speaking, we don't know what clusters to expect, and therefore we don't have any labeled data. If we had labels, no clustering is required in the first place, right? So we needed to find another way to evaluate GMVAE's performance on unlabeled data. For a GMVAE model, we generated 500 chunks from each learned cluster. So for example, here's the learned cluster 1, and we sample 300 chunks for training, and 200 chunks for validation. Using the training chunks and their cluster labels, we trained a multi-layer perceptron, or MLP, for classification. We then define a cluster as p% disentangled from other clusters if the MLP achieves p% accuracy on the validation set of that cluster. Intuitively, a set of clusters is more meaningful if they're disjoint, and we hope the concept of disentanglement captures this intuition. For a cluster, we refer to 70% or higher disentanglement as mediocre, 80% or higher as good, and 90% or higher as excellent. The plot shows the proportion of these three categories of clusters against the total number of clusters for three games mentioned previously. These proportions drop drastically as the number of clusters increases for the VAE GMMs, but are relatively high and stable for GMVAEs. We postulate that this is because the GMVAE can automatically adjust the granularity of the design patterns clustered by each learned cluster. Finally, let's talk about our contribution in prior work. Clustering means to categorize levels or chunks in an unsupervised manner. The two papers below involve the application of classic clustering algorithms. But note that they directly applied clustering on the levels and chunks themselves, while the GMVAE clusters the more latent, more compact features of chunks. In the past, conditional generation has been done by doing latent vector evolution in the latent space of VAE or GAN, or using conditional VAE or GAN. Note that these methods require prior knowledge either in the form of manually designed finesse functions or class labels. In short, our contribution is that we leverage the learned clusters to perform conditional generation, which requires no human knowledge other than the chunks themselves, but this comes at the cost of having to interpret the learned clusters.